Hi, everyone. I'm Scott Callaghan. I'm a computer scientist at the Southern California Earthquake Center. And I'm going to be talking today about how we at the Earthquake Center, or at SCEC for short, have been using Pegasus workflows to facilitate our large-scale seismic hazard analysis project. So I'm going to start by talking a little bit about the science, kind of explain what we're doing, go into some of the computational challenges we've encountered, and explain how we've been able to use Pegasus to resolve those challenges, and conclude with what I think are some kind of interesting scientific results. So, as I said, I've got this seismic hazard analysis in the title of my talk. What does that mean? Well, let's say you're interested in building a skyscraper in downtown Los Angeles, and you want to know how strong you need to build this building in order to withstand earthquakes. Ideally, you'd like to be able to go to an almanac or something and say, okay, I see in 2042, there's going to be a magnitude 7, so I better be ready for that one. And then in 2056, there's going to be a magnitude 6.4. So, I designed for those and great. But unfortunately, right, earthquake prediction is still an unsolved problem. So we can't do that yet. But we can take a probabilistic approach to it. You kind of do this anyway, probably, when you're thinking about earthquakes. For instance, you know that there's more earthquake hazard in California than there is in, say, Minnesota, right? You know that there are more earthquakes in California and that they're more likely than the ones in Minnesota. And so we can come up with a way to kind of formalize and quantify that, and then be able to offer some forecasts about the kinds of earthquake shaking that you can expect. So this kind of information is useful not only if you're trying to build a building, but also if you're trying to set insurance rates or in general do earthquake disaster planning. The approach for this is fairly simple. You take a list of all the possible earthquakes that might happen. For each earthquake in that list, you then figure out if this earthquake occurs, how much shaking will it cause? And then you combine those shaking levels with the probability that each earthquake occurs to produce what we call a hazard curve, like the one you see here in the middle of the plot. So on the x-axis, you've got shaking. In this case, the units are acceleration due to g. The y-axis is the probability, and it kind of has the trend you'd expect. You see that it goes from, we have a high probability of not very much shaking down to a low probability of a lot of shaking. And so if you're interested in building this building in LA, you'd look at the 2% and 50-year level, and you'd see that you need to build your building strong enough to withstand 0.4 Gs of acceleration. You can then also use this curve to fill in a single dot on the map over here. But if you want to generate a hazard map for the entire country, you need to repeat this process over and over for a lot of different locations. So the tricky part of doing this kind of processing, this analysis, is step number 2 here. If I give you an earthquake, how do you figure out how much shaking it's going to cause for your building or your location of interest? And there are a number of different ways that you can do that. But the approach that we're going to talk about today uses a high-performance computing and simulation to do so in what we call the CyberShake project. And so CyberShake was developed by SCEC, and what it does is it does wave propagation simulations to determine for each earthquake how much shaking it's going to cause. For a typical location in California, we're looking at simulating about 500,000 earthquakes, getting maximum amounts of shaking, and then combining those shakings with the probabilities to produce hazard curves like the one I showed you on the previous slide. Typically, we're interested in not just a hazard in one location, but for a whole region. And so in order to do a regional calculation, we have to repeat the process for several hundred locations. So for example, for this Southern California regional hazard map here on the right, I don't know if you can see it or not, but every of those little white triangles represents a location that we've gone through this whole analysis process for. So computationally, what's required? For a single location, the requirements aren't too intense. But when you start talking about doing an entire regional study, you see the requirements grow pretty rapidly, right? We're talking over 50 million compute hours, half a petabyte of data. So we're talking about doing large-scale simulations in order to accomplish this work. This isn't something where I can just sit down and submit a single job to a cluster, right, and have this finish. We have to have work running around the clock for weeks or months at a time in order to complete one of these regional studies. And so in order to do that, we rely heavily on our scientific workflow tools. So for us, we use Pegasus, of course, with HT Condor as our execution engine. Because of our large computational requirements, we typically target large NSF and DOE-funded supercomputers. However, we are orchestrating our workflows, so we're coordinating their execution from a server that's located at USC. So one of the challenges we have then is how do you send jobs over the network to be able to get through all of these compute requirements in a reasonable period of time? A second challenge we've experienced is that CyberShake consists of a lot of different codes. It is something like 18 codes written by 7 developers. And so they're all over the map. Some of them are large parallel CPU and GPU jobs. We have some quick serial post-processing jobs. And we also have some high throughput tasks. And this is another challenge for us, is how do we get through those high throughput tasks quickly so that we're able to accomplish these large calculations. And so I'm going to talk in a little more detail about these two particular challenges. So the remote job submission. In order to accomplish our regional calculations, we needed to execute thousands of jobs on large clusters located somewhere else. And so we've used 2 primary approaches in order to do this, both of which are supported by Pegasus. The first are what we call a push-based approach. And this is, I think, for a lot of people, kind of the default about how you think about getting things to run. And so the idea here is you have a task that needs to run, and then you go out and you find resources somewhere to run it for you. The question is, how do you get your task to the remote system to run? The easy way to do this is SSH, right? But I know we talked about this a little on Tuesday. One of the challenges is that a lot of clusters now are moving to 2-factor authentication. They won't accept an SSH key. And so then the problem is, if you're trying to make this automated, right, and it's 2-factor authentication, you're stuck. You have to have somebody there entering their fob information every time you want to run a job. And that doesn't scale very well, right? And I don't want to get up at 3 in the morning to have to put my key in. So instead, the Pegasus team developed an alternate approach that we've had a lot of success with. It's called RVGAP. And the way that it works is you start up a daemon on the remote cluster, and it connects back to your workflow submission host. And then you can use this connection to send jobs over the network. Since the authentication goes from the cluster to your workflow submission host, which hopefully you have a friendly system administrator in charge of, you have control over how that authentication is done. And as a result, you don't have to worry about the 2-factor authentication to the cluster. And so this approach has been very successful for us, and we've run many jobs this way. There's a second approach, also supported by Pegasus, that we've also used in running our workflows in concert with the push-based approach, and that we call pull-based. This is the approach that uses, some people refer to them as pilot jobs. If you're using Condor, you might have heard them called glide-ins. And the idea here is essentially you do it in reverse order. You start by getting your compute resources. And then once you have resources, you see, okay, what work do I have that I can pull onto these resources to execute? One advantage of this approach, of course, is you don't have the 2-factor authentication problem because you're getting the resources first and then you're matching work with them. A downside is that this approach can result in some additional overhead. So since you start up your job on the cluster first, you have your resources and you're being charged for those resources while you're figuring out if there's work to be run on them. You can also run into kind of a mismatch problem. So for example, let's say I request 200 nodes for an hour on my cluster, but then it turns out I only have 100 nodes for half an hour worth of work to do, right? The rest of that time I'm being charged for, it's being deducted from my allocation, but I'm not getting useful work done. However, there's a big advantage to this approach, which is one of the reasons that we've used it for executing our jobs, and that is that you can do bundling. So for instance, I could request 1,000 nodes on the cluster, and then I could run 10 of my 100 node jobs in those 1,000 nodes all at the same time across multiple workflows. One of the reasons this has been particularly useful is that we've discovered some clusters have their schedulers set up so that they favor larger jobs, right? Like the requirement for the system is that it prefer larger jobs. And so big jobs will actually start earlier than smaller jobs. So we can request a big chunk of nodes, 1,000 or even more, run many of our smaller jobs in that big chunk of jobs and get better throughput, helping us reduce our overall time to solution. So kind of the combination of both of these approaches and Pegasus support for them has been really important for us to be able to get our CyberShake results in a reasonable period of time. The second topic I wanted to discuss is running our high throughput tasks. So in this last year, in 2020, we added a new capability to our CyberShake workflows to calculate higher frequencies, so higher seismic frequency results. So basically, we take the original results that we produce and we augment them with higher frequency content. It turns out this is really important for building engineers. A lot of buildings are more sensitive to higher frequency ground motions. And so including that in our results makes our results overall more useful. Computationally, what's required to do this is the execution of about 75,000 more tasks. And so these jobs, these tasks are serial, and they're pretty short in duration. The shortest ones are just a couple of seconds. The longest ones are maybe half an hour. So how do we run these quickly? Well, we can't just submit them to the scheduler on the cluster, right? There are a couple of reasons. One is that usually there are policies. You can't put maybe more than 50 jobs in the queue at a time. And the other problem is that schedulers usually have a cycle of about 5 minutes. So what would happen, right, is you'd put your 52-second jobs in the queue, they'd start up, they'd exit, and now you have to wait 4 minutes and 58 seconds before another set of jobs can run. And so it's not practical for getting this work done quickly. You could, of course, use an approach like Glidance, but then you're really just switching the problem, right? Instead of it being a cluster scheduler problem, it's a Condor scheduler problem. You have more knobs that you can turn on that, but you're still going to run into some of the same problems. And so what we've used is one of the tools that ships with Pegasus, and that's a Pegasus MPI cluster, or PMC for short. And so PMC is an MPI wrapper, so a parallel wrapper, around your set of serial tasks. And uses a master worker paradigm. So it starts up, it has a master process that has a list of the tasks that need to run. And these tasks can have dependencies. It will take a DAG, so it can have the same kind of dependency structure that a normal Pegasus workflow would have. And then the master takes its tasks, sends them out to the workers to run. When the workers finish, they call back for more work. If for some reason things fail, then it writes a rescue file so you can start where you left off. It also enables you to use some intelligent scheduling. So one thing that we found really useful is that it will allow us to say about how much memory each task is going to require. Our jobs vary widely in the amount of memory they need. So being able to do this means that we can kind of pack the nodes as tightly as possible without worrying about over allocating the memory that's available. The other thing that's been really useful is, it's true with all the Pegasus tools, right, is that you as the workflow developer don't have to do anything custom to your application code in order to get it to run. I just have to say, okay, this list of tasks, I want to run these in PMC mode, and then Pegasus creates the list of tasks, does the wrapping, fires up the MPI job, and handles all that for me. And it means that we're actually able to get through these jobs very quickly. Because now, right, instead of having a scheduler, whether it's a cluster scheduler or a Condor do it, you're doing all of this coordination over MPI, which is very fast. And so we're able to get through our work in a short period of time. So just to give you a sense as to the kind of scales that we've been able to run at using Pegasus, our most recent regional calculation for CyberShake was done in the San Francisco Bay Area. It took us over 4 months of running constantly around the clock. In that time, we consumed about 120 million core hours of compute time. So this is 2,000 nodes constantly for 4 months. We ran 40,000 jobs across 3 different systems, across 2 remote clusters, and then we also ran some local jobs on our USC server. Pegasus managed over a petabyte of data for us. About 150 terabytes was transferred automatically with Pegasus Transfer. This was particularly useful for us because sometimes we would run part of a workflow on one supercomputer and then part on another, because sometimes one would have more load. Some systems have more GPUs, some have more CPUs, and so because of the automatic transfers, right, we can run part of the workflow here, the data gets transferred over, we run part of it here, the data gets transferred back somewhere else. And so this capability is really important for us to be able to get good throughput. In the end, we had about 14 terabytes of data. I think it was something like 12 million files that we copied back for archiving and that were registered using the Pegasus tools. So I just put this up here to say that really, these tools will scale to run very large calculations for a long period of time. One of the things that I think is kind of interesting about this result over here on the right, when I started working for SCEC, I kind of thought, okay, are people in California at risk due to earthquakes? Yes, right, full stop. But one of the things that we learned from doing a calculation like this is how much regional variability there is, right? If you take a look at this hazard map over here, right? Again, this is San Francisco. This is San Francisco Bay right here. You'll see that there are areas of very high hazard, these areas of bright red, that are, you know, in some cases just a couple of kilometers from areas with much lower hazard. And so producing these kinds of hazard results enable us to provide very specific recommendations at which regions, you know, really need to be prepared for larger ground motions as compared to others, and just in general improve societal preparedness for the large earthquakes that we know are going to come. So for us, the future directions that we're looking at, we have a couple. One is we're planning to do one of these large regional studies like I just showed, but with the new slate of high throughput jobs. And so we anticipate relying very heavily on Pegasus MPI cluster to support that. We're curious about doing some co-scheduling. So we have GPU, large parallel GPU jobs. We have large parallel CPU jobs. Could we run them at the same time on the same nodes? And that way we could improve our resource utilization, right? We wouldn't have to get two sets of nodes and be charged for both of them to run these jobs. And so we're wondering if there's, you know, maybe something clever we can do with glidings to kind of support this. But that's something else we're interested in looking at this year. And lastly, we continue to target new systems. Because our calculations are quite large, we continue to migrate CyberShake to the largest available systems that we have access to. And so in the 14 years that we have had CyberShake, we've run it on 12 different systems. And this is another advantage of Pegasus that has been really key for us, is that once we have our DAX generator, once we create our abstract workflow description, right, we can run that on any system. Right? All we have to do is make some edits to the catalogs that, you know, Raphael mentioned in his talk, the site catalog, the transformation catalog, and set things up, you know, make those few custom changes for that system, and then we're ready to go. And so having this capability has been really important in enabling us to continue to run CyberShake on the largest machines that we have access to. So I'll finish with some feedback. In general, with CyberShake, every time we run the calculation for a single location, we're running about 5 separate workflows. So when we're talking about running a regional study, we're looking at running, you know, over 1,000 different workflows. And so for us, kind of additional tools that help us manage things across workflows are useful. You know, Ryan's talk on Tuesday reminded me that the ensemble manager, you know, has come a long way, and that I think is definitely something that, you know, we need to take a serious look at and see if that would help us out. Something like that would help us kind of manage the campaign in its entirety, right? How many workflows have we run? What do we have left? Make sure that we have a certain number running it at all times, kind of tools like that. The other challenge we've confronted has to do with load balancing. So as I mentioned, we often are running in multiple clusters at the same time. And so we want to make sure, for instance, that all the clusters have enough work, but not too much. This is especially important because sometimes we have reservations on these systems, and so we have to keep a minimum amount of work running at all times. A related challenge we face with load balancing is that sometimes we have stages that can become a bottleneck. So for example, one of the stages near the end of our workflows is to take our output data and put it in a database. Well, what can happen is if we have multiple workflows that all get to that same stage, then they start competing for the database write bandwidth, right? And then those jobs start to slow down. And then more workflows come in with their database write jobs. And then that makes the problem worse. And we can end up in a situation where practically all of our workflows are stuck waiting to write to the database and nothing else is running. So, you know, if there's a possibility of kind of additional tools to be able to tweak that or control that, or say, okay, let's only have 5 jobs, regardless of what workflow they're in this stage at a time, I think that would also help us out. But I want to thank you for the opportunity to talk about our work and, you know, acknowledgements to our funding agencies and our compute providers.